8,000 plus students, 400 plus faculty, 3,000 plus placements, 100 plus companies. Green campus with latest infrastructure. Industry institute collaborations. Techno and cultural fests. Ranked among top engineering colleges in the state, SB Engineering College for Women is now SBEC with co-education. SB Colleges, Tirupati.
Good afternoon, one and all present here. Once again, I welcome all the participants to this 5-day short-term training program. Now we are going to start this second session. Once again, I thank you for joining with us. I request our resource person, sir, please stop your presentation for time being, sir. We will give a warm introduction for you, then you can present, sir. Please, sir. I request Dr. Jayakrishna, sir. Sir, Rajesh, sir, now you can share, sir. Yes. We are honored being joining with this Dr. Jayakrishna, sir. Thank you, sir. Now, Dr. K. Jayakrishna, sir, professor from the Vellore Institute of Technology. He is going to continue a session with introduction to nanomaterials. Dr. Jayakrishna, sir, research is focused on the design and management of manufacturing systems and supply chains to enhance efficiency, productivity. Sir, requesting, sir, Jayakrishna, sir. Sir, time being, we are introducing your profile, sir. Please stop sharing, sir.
Sir, Madhivana, sir.
Yes, sir. Yes, sir. Shall I continue, sir?
No, sir. Please wait, sir.
Sir, let me continue, sir. Thank you, sir. Dr. Jayakrishna, sir.
No, sir. Sir, Madhivana, sir. Sorry, sir.
Yes, sir.
There is some small technical issue with sir.
Okay.
We will wait, sir. Please, sir.
Okay. No problem.
Thank you, sir.
Thank you.
Okay. 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 My voice is also there, no?
Yes, sir. Your voice is audible, sir.
Okay. Sure. So. Okay. So. Okay. So now you will start, and then after that I'll go to present now and start presenting.
Yes, sir. Yes, sir. Let me
Okay.
complete your introduction, sir, please.
Okay. Okay. Thank you. Thank you.
Rajesh, sir, shall I start now, sir?
Yes, sir. Yes, sir.
Yes. Thank you, sir. Today, second day, second section presentation will be handled by Dr. K. Jayakrishna, sir, Professor, Vellore Institute of Technology. Dr. Jayakrishna, sir, research is focused on the design and management of manufacturing systems and supply chains to enhance efficiency, productivity, and sustainability performance. He has mentored many undergraduate, graduate students. He has published more than 43 journal publications in leading SCI Scopus indexed journals, 22 book chapters, and 85 refereed conference proceedings. He has also been awarded with Institution of Engineers Young Engineer Award in 2019 and a Distinguished Researcher Award in the field of Sustainable Systems Engineering in 2019 by International Institute of Organized Research. SAR has published more than books in international level, and he has published 4 patents and with the citation 600. Sir, we are very much honored, sir, for being a part of this program. Thank you very much, sir. Sir, I request our resource person to continue this session, sir. Thank you, sir.
Yeah.
Yes.
Thank you, Modi sir. Thank you so much for a nice introduction. And I could see around like more than 120 participants in this right now. Okay. So let me start the presentation, or should I wait for because we have promised from 2 to 4. So should I start now, or it's up to your advice? Should I start now, or should we wait for 2-3 minutes?
Sir, we wait for 3 minutes, sir.
Okay. Okay, we'll do that.
Sir, I requested to all participants kindly switch off your video, sir.
So my slides are visible?
No, sir. No, sir.
No, sir, it is not visible, sir.
Okay. Maybe now?
Yes, sir. Yes, sir.
Okay, thank you.
Now visible, sir.
Okay,
Yes, sir.
thank you. Thank you. Sorry, this is the first time I'm going with Google Meet. Only once I have attended a conference call, but this is the first time I'm presenting using Google Meet. So maybe slowly I will catch up with the technology.
Thank you, sir. Now it is visible, sir. Perfect, sir.
Okay. Okay, good morning. I think it's 2 o'clock and I think we can go, right? Shall we start?
Yes, sir.
Okay, thank you. So my slides are visible now. Again, I have reshared it.
Yes, sir.
Yes.
Visible, sir.
Yes, sir. Visible, sir.
Thank you so much.
Sir, 1 minute, sir. I request all the participants, please mute your video and mic also. Please, I requesting once again to conduct this program very smoothly. Thank you, sir. Now you can proceed, sir. Please.
Yeah. Thank you. Thank you for the I thank for the wonderful introduction what that has given to me. And I am Jai Krishna, and I am I'm associate professor associated with VIT University Vellore. And today we will be discussing in this AICTE sponsored workshop on about nanoparticles and its application, especially in combustion tribology. But my focus today is going to be on overall about nanoparticles, how they are synthesized, and what are the applications that, by using nanoparticles. So this is going to be my primary objective of today's discussion. Okay, so let's start slowly and let's get introduced. So as I move on, I think I will slowly I will switch off my video for better quality and streaming. So as we start, so we all know that nanoparticles. So when I say nanoparticles, everyone knows that nanometer. I mean, nano means very, very small. But why it's to be small, and what are the definition of this? So nanoparticle, as I say, it's an ultra fine unit with dimensions measured less than nanometers. So normally 1 nanometer is how much? 10⁻⁹ meter. So nano means it's going to be very, very small. As we all know that it's going to be a very ultra fine unit, very, very small unit. Okay. So next, International Organization for Standardization, ISO. We call it as ISO, International Standardized Organization, or Organization for Standards. Okay. They are given the word ISO because ISO means uniform. So that's why instead of IOS, they are given it as ISO. So why they are defining it as how they define a nanoparticle is based upon the dimensions. What is it going to say? So Cartesian dimensions, that is X, Y, Z. So whenever you are going to measure a nanoparticle in all the axes X, Y, and Z, in all the direction of measurement, it is going to give us only 100 nanometer. That means the size of the particle is going to be less than 100 nanometer. So that means, see how much small it is going to be. It's going to be very, very small, 100 nanometers only. If you measure along X, Y, or Z, all the 3 axes. Okay, X, Y, and Z. So if you're measuring the particle, it is going to be only 100 nanometers or less than 100 nanometers when you measure this. Okay, so again, there are different types of nanoparticles as defined by ISO. There are 2 things. One is called as 2D and another one is 1D. What is 2D? 2D means we call it as nano objects. So nano objects here, I mean nanofibers and nanotubes. Nanofibers, fiber, it's like just like a small hair. One hair, it will be we call it as nanofiber. But nanofiber, it's, for example, I'm telling you, but nano means much smaller than that also. And nanotubes, we will discuss all these things in the upcoming slides. Then we have one-dimensional nano objects. We call them as nanodisk or nanoplates. Like normally we know, when I say nanodisk or nanoplate, you can remember the simple example of our solar panels. The solar panels are the silicon wafers, what you find in the what you observe in the okay. So what you observe in the solar panel. So that can be the one example for one dimensional object. So that is it. So next we will look at what are the types again. How a nanoparticle will look, all these things. Okay. So nanoparticles means it's not a single thing. It's a combination of some molecules or atoms. Then we have 3 layers. Normally, if we say a nanoparticle, it is going to have 3 layers. So the first layer is called as a surface layer. First layer means imagine a ball. The first layer, the outer layer, we call it as a surface layer. A cricket ball or any ball you can assume. The outer layer we call it as the surface layer. So in the surface layer, what happens? There are going to be a lot of small, there's going to be interaction happening, because since that is the surface layer is just like our skin. like how humans have skin. Similarly, nanoparticle, they will have a skin. In that skin, they will have small molecules. Okay, that is made up of small molecules and metal ions, surfactants, and polymers. Okay, this surfactants these are going to have this surface layer is where lot of reactions are going to happen. Okay, a lot of endothermic reactions are going to happen. So, which will change the property of the nanomaterial, or it may increase or what I'm meaning is it can increase or decrease. It can increase or decrease the property of the nanoparticle. Then the next layer is called the shell layer. Okay, this shell layer will have some different chemical material. Okay, this is going to have some chemical made of some chemical different material. But this chemical material are not of the core, because core is also made up of some material, but the shell layer will be of different material. Okay, just when I say the size of when we define an atom, anions, all these things, it's just something similar to that. Okay, then we have
Excuse me, sir.
Yeah.
Sir, your slides are not visible on the screen.
Okay, sorry.
Excuse me, sir. It is visible, sir.
Sir, it is visible. I request participant, please identify.
You have to pin yourself, sir.
Yes, you have to please pin resource person's screen. Slide will be visible. Perfect. Sir, you can proceed, sir. It is okay. Sir.
Okay. Thank you. Okay. Thank you. I can understand some technology hiccups are there. Okay, let's slowly catch up. No problem. Okay. So others also, if slide is not visible, do as per the instruction of the organizers. Okay. So I told you the nanoparticles are made up of 3 layers. The first outer layer is called the surface layer. Then we have the shell layer, which is hollow in nature mostly. Mostly it's hollow in nature. Then we have the central layer or the core layer, which is made up of certain proportions of the nanoparticle. So to understand a nanoparticle, we should know what is surface layer, what is shell layer, and what is core layer. So it is going to be in 3 levels. Okay, just we say when we say the structure of the earth, we know the surface, the core layer, and middle we have a magma layer, all these things, right? So that's similar to that. If you know geography of earth, that is something similar to the structure of a nanoparticle. Okay, so how based upon this structural arrangements, a nanoparticle is again classified into 2. Majorly, it's going to be classified into 2 types. One is organic nanomaterials. The other one we call it as inorganic nanomaterials. So in organic nanomaterials, there are different types. So again, we have several types. The major types of organic nanoparticles are polymeric nanosphere, polymeric nanocapsule, polymeric micelle, liposome, and dendrimer. Then in inorganic nanoparticles, we have mesoporous silica nanoparticles, carbon nanotubes, iron oxide nanoparticle, gold nanoparticle, and quantum dot. Okay, so participants can mute yourself so that I don't want to hear my voice again back. Sorry for that. Okay, so let's discuss one by one now. So we normally we have 2 types. One is called as nanos. If you observe this slide, you will find there are 2 things. One is nanosphere and nanocapsules. The first type, the polymeric nanosphere or nanocapsules. So what are this? So these are normally made up of solid polymers. These are made up of solid polymers of organic matters, which are embedded in a polymer matrix. Okay, if you know about composites, I think this is very easy to understand. We say composite. Generally, a composite, what we say, we have a matrix. Matrix means when I say composites, we always go with the concrete. Okay, the simple example, if you ask anyone what is composite, they'll give you the example of concrete. So in concrete, the steel wires, steel rods, what we place inside, we call them as reinforcements, and the mixture what we provide as the matrix. That the cement and the other mixtures what we add, that we call as the matrix. To keep it very simple for everyone to understand. So same way, this nanosphere or nanocapsules are going to be made up of solid polymers which are embedded in a polymer matrix. Okay, so these polymers are now embedded in a polymer matrix, and what they're going to do, and if they normally use for carrying. In case of biomedical application, they will be used for carrying some drugs. As you know, these are organic matters. Normally all these nanoparticles will have biomedical applications. They're studied for their biological properties and how drug can be delivered to your body. I think everyone must have taken a capsule medicine, right? During our fever or common cold, there will be a capsule. Okay, so I think influenced by that, people started producing nano capsules. There will be a top and bottom layer, and inside you have medicines. Same structure only. This nanoparticle is going to have. It's going to outer layer, and inside it will be hollow, where you can place the drug which you want to deliver to your body to the respective to cure the respective diseases for which the drug can be a cure. Okay, so that's how it works. So when I say capsule, it is both these are going to act as small vesicles. Vesicles means like carriers, right? This is vesicles. So these are going to transport the drugs from the drugs inside our body or where it is going to be used. Okay, in case of nano capsules, it is going to be a shell type. It is going to be a shell type. Just imagine like a football. It's going to be a shell. But what happens? The inside the shell, it is going to be loaded with the inner space of the shell is going to be loaded with drugs. Okay, which are again embedded in the polymer matrix, and it's going to be delivered. Just imagine the example of a small capsule tablet. What you take. That is the influence for this nanosphere or nano capsules. Then we have something called as polymicelles. These polymicelles are again the nano carriers. Okay, the nano carriers. These are nano carriers by spontaneous arrangement of amphiphilic block copolymers in aqueous solution. That is, this is like these are more like a jelly kind of thing. Like if you see a jellyfish, you'll understand. Even the structure will sound similar to a jellyfish, where you find they are arranged in such a way that they are arranged like a ball, like a ball, where the core layer in the inside, the core layer is hydrophobic in nature, and the shell layer is hydrophilic in nature. You should know what is hydrophobic and hydrophilic. Hydrophobic means that is the core, the inner layer. The inner layer does not dissolve in water, or it does not accept water to pass through. Right, whereas this hydrophilic shell can be dissolvable in water. So what happens when you put something inside the core? Okay, the something inside the core which is hydrophobic, the outer layer is going to get dissolved, and you can use the inner layer as a medicine. So that is the idea. So same like our capsule. When you eat a capsule tablet, what happens? The outer layer dissolves. The medicine, whatever is present inside the capsule, get accumulated or get transferred in our body cells or carried away. So that's what we call this as drug delivery nanoparticles. They are mostly used for drug delivery. So the next type we call as liposome. What is this liposome? These are again the tiny bubble of vesicles used for drug delivery, and these are filled again the same way. It is again filled with the drugs or the nutrients what is necessary. If you see the head part, this part, if you could see the movement of my cursor, the blue color we call as heads, and we have a tail. Okay, head. So here the outside part is hydrophilic, and the tail part is hydrophobic. Okay, this tail part is hydrophobic. Mostly all these protein supplements will have this liposome kind of structure. Then we have dendrimer. Dendrimer we call that as these are repetitively branched molecules. We also call it as absorbs or cascade molecules. You could see a single molecule like these are like a hair-like structures. So we call it the dendrimer. Okay, so these are like a tentacles of an octopus. Like they can go and go and adhere to any body part very easily. So these are the types of organic nanoparticles. Okay, so I think we are speaking more about chemistry today in today's guest lecture. So next we have inorganic nanoparticles. In first type we have mesoporous silica nanoparticle. This is the example of a mesoporous silica nanoparticle. These have high stability, larger surface area, and these are the pore sizes, like this pore sizes, whatever you see here, these pore sizes are controllable by the size and volume. You can control this, or you can tune the size of the pores and volume of this surface volume or the surface area of this. You can control. Okay, these can easily encapsulate the drugs and proteins and used for biogenic molecules. It can hold drugs, proteins, and biogenic molecules inside this, and this is also used for drug delivery. So imagine, I guess, if you know this, okay, to give it as a simple example how this will look like, you can take an example of a rasagulla or a gulab jamun. So what happens there, you will find minute pores where inside you have the sugar juice content, sugar content, right? So that is visible. So this is something similar to that. Imagine like that. Okay, imagine like a food item, so that after post lunch you will remember nice gulab jamun. So right, this is a gulab jamun kind of thing where you can control the surface volume, the drug with what in the sugar content what is going to carry, the protein value what it is going to carry. So these particles are something like that, made up of silica. Okay, that's what we call it, means silica nanoparticles. Next thing we have is what we have is called as the carbon nanotubes. Okay, carbon nanotubes, of course we are going to discuss that more in detail in this lecture. Carbon nanotubes are nothing but the graphene sheets rolled up together. So graphene sheets rolled up together, which have a lot of carbon in it. Okay, of course made up of carbon. Okay, that's what we call as carbon nanotubes. I will keep this for the rest of the class. I mean, the upcoming slides I will discuss about this carbon nanotubes. Next, the type what we have is iron oxide nanoparticles. These iron oxide nanoparticles are normally in the range of 1 to 100 nanometers. I repeat, it's in the range of 1 to 100 nanometers. Why they are called iron oxide? Because they are made up of magnetic ferrous Fe3O4. The formula is Fe3O4. It's made of ferrous oxide. A lot of oxides are there. So there's oxidized magmite where Fe2O3. So ferrous oxide, mostly it's made up of ferrous oxide. This nanoparticle is made up of ferrous oxide. So that's what we call it as iron oxide nanoparticle. Next we have gold nanoparticle. Again, this is also the range of 1 to 100 nanometers. This gold nanoparticles we call it as AuNP. AU is the formula for gold, right? So AU nanoparticles, and these particles are normally small in size, and when dispersed in water, they form colloidal gold. Like aqueous gold, like a liquid gold, like aqueous gold, right? So they are going to be so normally you find this gold nanoparticle applications in all your electronic gadgets, even in a SIM card. You have in electronics, you'll find in photodynamic therapy, you'll find it in therapeutic as therapeutic agents, you'll find it in sensors, sensor probes, scanning probes. You'll find it used in catalyst for several diagnostic, and again in several diagnostic applications you'll find this gold particle. Okay, next we have something called as quantum dot. You will all be excited to know what is quantum dot. This quantum dot, of course, many of you must have known already. Quantum dot is a tiny nanocrystal. Okay, it's a tiny nanocrystal. What happens in this quantum dot is where you find this quantum dot is, you will find in your solar panels, TV cells, and TVs, especially in LCD liquid crystal display TVs. You will find this quantum dots more in number, and it is also used for some medical applications. So what is this quantum dots? Okay, so what is it? This is a white. What happens is, these are nanocrystals. We call this tiny nanocrystals, which when light falls on this, they will emit white. They are going to give white light. Okay, they are going to emit white light. So what happens normally in a LCD screen? What happens? There are a lot of blue LEDs placed behind the screen. Okay, there is a different layers of arrangement of your LCD screen. Now try to follow my what I'm talking, so that you will understand what is this quantum dot. So in this quantum dot, there is a LCD screen. Above this LCD screen, behind this LCD screen, what do you look? There is if you see in your TV, there is a arrangement of blue LEDs. These blue LEDs, next layer there's a layer of blue LEDs. Next we have this layer of quantum dots. Then we have the layer of the primary colors. You know, primary colors are red, green, and blue. Okay, so what happens now when this light, when the blue LED passes the light through this quantum dots, it gives out white light. pure white light. When this white light is again passes through this RGB layer, that is a green, red, red, green, and blue, whatever. Okay, RGB layer. What happens? It gives us very clear picture. Okay, since it's like this quantum dots are going to act as a filter for the light what is being emitted, and it passes through the RGB. In regular TVs, you don't have this. If you're not having this quantum dots, it will be a normal TV what we watched in our 80s and 90s, the big TVs. So this quantum dots is giving us a LCD view. Even it's available in our mobile phones. So what happens? Again, you see Sony is telling it giving this many colors, and you see Samsung, this LG TVs, they're all coming out with this LCD TVs using this quantum dot technology. So now you'll know why this is LCDs are the picture quality of LCD screens are higher, because nanotechnology is there. We have quantum dots in the LCD screens. Okay, so this is one. These are the types of nanoparticle. I think I have explained to you enough of this nanoparticles. Now let's see. Let's go a bit deep into this. Okay, again, nanoparticles are divided into various categories depending upon their morphology, size, and chemical properties. As I told you, they are going to be classified based upon morphology or the arrangement of the atoms in it, size, and chemical properties. Okay, so depending upon this, the nanoparticles are classified morphology, size, and chemical properties. Okay, next we'll look upon each and every the different types of nanoparticles. The first kind of nanoparticles we are going to call it as or carbon-based nanoparticles. First, we look into the carbon-based nanoparticles. In this carbon-based nanoparticles, we are going to discuss about the fullerenes and carbon nanotubes, that is CNTs. In short, we call carbon nanotubes as CNTs. Okay, what is this fullerenes? These fullerenes. Imagine a football. Okay, imagine a football. You know the structure of a football. The structure of the football will be something similar to the structure what you're looking into your slide. You can see that in this slide, you could see the blue color ball, small blue color balls. Imagine that as a carbon atoms. So imagine this structure: 1, 2, 3, 4, 5. So this forms a pentagon-like structure. This forms a pentagon-like structure. So, but you observe this side. The next is this side: 1, 2, 3, 4, 5, 6. So one where it is forming a pentagon structure, the other side, the adjacent thing, it's taking the structure of the arrangement is in a hexagon pattern. So you will know that fullerenes are in normally when we speak about carbon, where the allotropes of carbon are generally we call them as gold and graphites. Okay, graphites and diamond, right? So all this, only these two things are considered as allotropes of pure allotropes of carbon. But we have one more thing called as fullerenes. This fullerenes looks like as I told you, this is going to be taking the shape of a pentagon or hexagon. So why this is happening? So there is one scientist by name Buckminster Fullerene. So from his name, since he invented this third type of allotrope of carbon, we call this as fullerenes. So he named he also called this as buckyball. Okay, he also called this as buckyballs. Now listen to this: buckyballs. So I'm speaking about buckyballs. Okay, why? Because if you take this ball like what I shown in the figure in the slide, if you observe this ball, there is going to be 60 carbons. 60 carbons will be there. What if you count the number of carbons? It's going to be 60 in number. 60. I repeat, 60. Okay, so the number of carbons in this is going to be 60. And if you see this is going to be looking like a cage, a spherical cage. Okay, that's why we call this as a ball. And since it is named after a Buckminster fullerenes, it's called as fullerene cage or fullerene ball, or it's also called as buckyball, because it has 6 things. So here you will find both pentagon shape and hexagon shape of arrangement of carbon units. Okay, and if you take this again, this is going to be sp square hybridized. That is the second level of hybridization. You will find this kind of arrangement. Okay, so where I can find this? Okay. So here, if you see, the structure is going to be purely hollow in nature. If you observe this fluorines, the structure is purely hollow, and it is made up of pure carbon molecules. So the number of carbon molecules is so much, it's going to be 60. Okay, so these carbon atoms lie at the vertices of polyhedron units with 12 pentagonal faces. There will be 12 pentagon. Okay, if you count the number of pentagons, it's going to be 12 pentagons, and remaining things is going to be your polyhedron. 12 pentagon shapes, and remaining is going to be your hexagonal faces. Okay, and here each carbon is bound to 3 other carbons. If you see, one carbon will be bound to minimum 3 carbons. Take this example. There's the one carbon which is bound to 3 carbon molecules. 1, 2, 3. Okay, minimum 3. It is going to be, each carbon is bound to only 3 carbon molecules. Okay, so and they will take a shape of a pentagon or hexagon, as I told you. So when you see this in the NMR spectrum, it will have a very good. You can find this 60 carbon molecules arranged in this setup. So I told you this is called as buckyball, named after the founder Buckminster fluorines. It's also called as fluorines ball, and it's having 60 carbon molecules. It is made up of 12 pentagonal arrangements, and remaining thing with hexagonal carbon units. And this is going to be a hollow cage-like structure. And this is the third allotrope of carbon, which was invented very late. So where will I found this? You know, when you boil, when you burn coal, you can, and if you collect the soot. You know, right? I don't think that you remember. Normally in villages or still in some houses, when a baby is there, they apply this kajal to them, right? So how they produce this kajal? They burn, they light up a small lamp, okay, and they will show a coconut shell above that. So what happens when the from the lamp, the smoke will go, and the smoke will deposited on the inside of the coconut shell, and after that they will pour some coconut oil or something like that, and they will scrub the shoot and they will apply it as kajal. Okay, you know that, right? So in some people house they used to do this for small kids. So because it's natural. Okay, but this the soot what you collected, that is called as fluorines. Okay, you understand that? So that is called as fluorines. Or simply, if you are burning something out of coal or wood, and if you are collecting the black color particle from the chimney, then that will have fluorines. So you see how easy it is, right, to collect the fluorines. Okay, and if you very well, if you could play with the carbon molecules, even you can end up making diamonds in your home itself. But of course, it's a difficult process. But just for example, I'm giving you. So soot means like the carbon particles, whatever you collected. So that is one example for common fluorines, what you can make in your home itself. Okay, next we are going to discuss about carbon-based nanoparticles. When I say carbon-based nanoparticles, we are going to have again the same carbon molecules, but in the diameter of 1 to 2 nanometers. Okay, 1 to 2 nanometers. Their arrangement is going to be only 1 to 2 nanometers. Imagine how small it is going to be, right? Very, very small. Okay, then how this can be predicted as metallic. Sometimes they're metallic, sometimes they're semiconducting, and they have a diameter helicity. That means they can expand and contract. Okay, they're just like they have elastic property, it seems. So that means its diameter is shrinkable and expandable depending upon the shape. So it's very simple structure. It's just the graphene. If you know structure of graphene, when you arrange the graphene and if you are able to roll that roll it, we get graphite. We get carbon nanotubes or carbon nanoparticles. Okay, so this is just going to be sheets. So if you found only one layer, we call that one roll of graphene. Then the graphite, sorry, not graphene, graphite. When we find only one layer of graphite sheet, then we call a single-walled carbon nanotube. If you find two roll of graphite sheet, then we are going to call as double-walled carbon nanotubes, and we have triple walled and such that depending upon the number of walls, just we are going to call it single walled, double walled, triple walled, quadra walled, whatever, right? So we have this is up to the necessity or the requirement. You can go with single walled carbon nanotubes or double walled carbon nanotubes. Now what happens? This carbon nanotubes or carbon nanoparticles, carbon-based nanoparticles, and when I say graphite, it is used for many of the applications, for structural applications, for tribological applications. Lot of carbon nanotubes are nowadays used. So that is one classic example. Next we know that how to produce this carbon nanotubes. So carbon nanotubes are generally produced by chemical vapor technology or chemical vapor deposition. We call it chemical CVD, chemical vapor deposition. One more thing also is that physical vapor deposition. But in this case, we are carbon nanoparticles are mostly produced, or CNTs are normally produced by using CVD technology. What is this CVD technology? We will discuss elaborately in the upcoming slides. So just now understand that these are going to be manufactured using carbon precursors. What is precursors mean? It's going to be the derivative of carbon. Okay, it's going to be the derivative of carbon. That's why it's called precursors. Okay, and it's going to be mostly what we're going to do is we are going to atomize, or we are going to evaporate this graphite, and we are by electric arc method, and we are going to produce the carbon nanotubes. Just now you remember that it's going to be a carbon precursor manufactured from graphite by using graphite and by using electric arc method. Just remember this thing. When we go into the process, I'll be explaining you clearly about this chemical vapor deposition technique. So why these things are used? Okay, why these carbon? You could see, if you could download any scientific papers related to composites or anything related to nanotechnology, now you will find out a lot of papers coming out with the use of CNTs. Now CNT is like a fancy word in the area of composites. Okay, you could find that due to because of the chemical, physical, and mechanical characteristics, these are used in pure forms. That is, carbon nanotubes are straight away used. They don't need to mix with anything. In its natural form itself, you can use nanocomposites for many commercial applications, especially for many commercial applications. They are using this, such as fillers. As I told you, in composites they are using as fillers, for sometimes for gas absorbance, for environmental remediations, and it is also using some as catalysts. In most of the inorganic and organic analysis, they are using as catalysts. Okay. Anyway, we are going to look in more deep into this applications of this carbon nanotubes in the upcoming slides. Okay, so as of now, I'm just skipping this slide because I want to show you a video, but I think that it's easy for me to proceed straight away, because anyway I'm going to explain this thing. Next we have metal nanoparticles. Okay, now so far we saw about carbon nanotubes and what in fluorines we saw about fluorines. Now we will start discussing about metal nanoparticles. These metal nanoparticles are purely from are derived from the metal precursors. Or metal precursor means it's a derivative of some metal. It's going to be the derivative of some metals. Okay, so but again, these are going to be manufactured by using localized surface plasmon resonance, right? These are going to be manufactured by localized surface plasmon resonance. What is this localized surface plasmon resonance? It is a phenomenon generated by a light wave trapped within conductive nanoparticles smaller than the wavelength of light. Okay, it is the result of the interactions between the incident light and the surface electrons in a conduction band. So it is like a particle which will be trapped inside the plasma, and it is going to be, you are going to produce that by using the metal precursors. Okay, and if you see, observe this is going to have a lot of optical properties. That's why you'll find these metal nanoparticles in many of applications where you use photo. Like photo means, like I assume, light. Wherever a lot of light sensitive applications are there, you will find this application of nanoparticles, metal nanoparticles. Okay, these are normally of alkali and noble metals, for example, copper, silver, and gold. So I told you, wherever light applications are, right, like if you're going to do something using light, you'll find this metal nanoparticles, and it is also visible in the electromagnetic solar spectrum. Like like solar spectrum. I don't want to go deep into the solar spectrum. So you will observe that. Okay, so you know this, right? So if you're working with composites, people will know about metal nanoparticles. They can understand this nanoparticles very easily. Their facet size and shape can be controlled easily by using any cutting edge materials, like any materials you can use this. So where you will find this, normally this gold NP coatings is widely used for sampling of SEM to understand the electronic stream, which helps in obtaining high quality SEM images. Whenever you are going to do take some SEM images for your PhD or whatever you for your research work, we coat that material using some gold, right? So gold nanoparticles will coat, because as I told you, this will show you the exact surface properties of the metal what you're going to study. So that's why whenever we are taking SEM images, we are going to use gold nanoparticles as coatings. Okay, so a small quantity will be applied to coat it. Okay, because why? Because I told you this is going to because wherever you find the light-based application, optoelectrical properties, not increase the optoelectrical properties, or to read that surface very easily, we will be coating that with gold nanoparticles. That's the reason we are coating, because of its optoelectrical properties. Okay, the next type of nanoparticles what we are going to see is called as ceramic nanoparticles. These are mostly inorganic or non-metallic solids. Okay, when I say non-metallic, you know what is that. So it is basically synthesized via heat and successive cooling, and this can be found in lot of things: amorphous, polycrystalline, dense. These are dense and sometimes porous and sometimes even hollow forms. Okay, they can these are like mostly like solid nanoparticles, and they can take shape of anything. Right? It can be sometimes amorphous, sometimes polycrystalline, sometimes dense, porous, and hollow forms also available. Okay, and why these are used? So these are used as mostly like catalysis and photocatalysis for photodegradation of dyes, because it has a lot of absorption properties. Then imaging applications, wherever it is there, you are using this ceramic nanoparticles. Even ceramic nanoparticles are used for tribological applications in more numbers. Then we have semiconductor nanoparticles. The moment when I say semiconductor, we are going to deal with conductivity. Okay, so semiconductor material possess properties between these are not metals or these are not non-metals. Their properties are going to be in the middle. They are going to be either metals or non-metals. We have semiconductor-based nanoparticles which possess very wide gaps, and this can be adjustable. Like this can be tuned to any level. That's why we prefer using semiconductor-based nanoparticles. Okay, and they have photocatalysis, photo optics, and electronic devices. So semiconductor, and of course we are going to discuss a lot of things only about semiconductor today. How we are going to produce this semiconductor-based nanoparticles or nanosynthesis technologies. So almost like all electronic goods, we are going to use semiconductor-based nanoparticles. The next type is called as polymeric nanoparticles. This polymeric nanoparticles, as we discussed, is going to be mostly organic based. 99% they are going to be organic based nanoparticles. Normally, as I told you, it's going to be nanocapsules or nanosphere. As in my previous discussion, I told you about nanospheres and nanocapsules. I told you there are going to be 3 layers. One is the surface layer, the other one is the shell layer, next one will be the core layer. Now you could see what are these, right? So the nanospheres, first you see this diagram, the nanospheres. In this nanospheres, we have the matrix where the solid particles are act as the core, and the you could see the polymers. This is the polymer matrix. Okay, this is the polymer matrix, and you will see the drugs inside the nanosphere. So this is a polymer matrix with drugs loaded. Okay, and the next case is called as nanocapsule, where you have the nanocapsule. As I told you, it's going to be the outer layer. Like I told you that it's going to be the outer layer. Right? The outer layer is something made up of polymers, and inside that it's loaded with the drugs. Okay, and what is this, right? So we have this to understand this, we should know surfactant and the emulsions, the emulsion properties and all these things. Okay, so to understand this, we should speak something about the paints and the detergents. Okay, you know that. Now listen to my discussion. What I'm discussing now. We use the detergent called as Surf Excel. But we don't know why we call it.
Sir, sorry, sir.
Yeah.
Sorry to disturb you, sir.
Please.
Sir, actually, our participants are feeling that slightly faster, sir. Can you reduce your speed, sir?
Yeah,
It seems
sure,
that,
sure.
yes,
Sure.
it will be good for others also. Thank you, sir. Thank you.
Okay, okay, okay.
Thank you, sir. Your presentation is very nice, sir. Please continue, sir. Thank you.
Okay, okay. Thank you. Thanks for noticing. Okay, so okay, so as I told you, like we are going to discuss about something about paints and detergents. We know we commonly in our house we use surf excel, right? We know surfactants. So just imagine that as a surfactants. So what happens to this surfactants? So you have a cloth and you are using that cloth. On that cloth, what happens? The dust particles or the particulate matters are getting stick. So we call, and after using that, we tell that okay, this cloth, after wearing for a few days, it will one day it is going to smell bad because, and it will look, the color will be looking something different because of the particulate matter deposition on the cloth. So what we do, this particulate matter means imagine dust particles. So the dust particles are going to adhere to the surface of the cloth by what we call that as the adhesive bonding. Okay, the bonding by the intermolecular force of attraction. This particle matters are going to get stuck to the cloth. So now what happens when you are using this detergents? These detergents are what? These are dipolar. Okay, these are dipolar. Okay, dipole means two things. Okay, so what happens? This dipole agents, they go and they kill or they suppress this intermolecular force of attraction between the cloth and the dust particles or the particulate matters. So what happens? These are called as surfactants. These surfactants go on are the dipolar agents which go and kill the intermolecular force of attraction, and because of that, what happens? The dust particles or the particle matters, they get dissolved or they get removed as we wash by using the water. Okay, same way these emulsions or this surfactants, what happens? This will be like a filmy layer. They are forming filmy layer carrying the drug with the polymer, and whenever they want whenever they are come in contact with the blood or something, they get dissolved and this enters the body. So this is the polymeric nanoparticles. Okay, so these are surfactants and polymers. So imagine that there is nothing but just imagine this your capsule, normal capsule tablet what you are taking. So that's the best example for this nano capsule or nanospherin. But imagine the size is very small. So mostly these are used for drug carrying applications. Okay, next we have again the same kind of thing for more biotechnology we are going to talk about. So that is called as lipid based nanoparticles. In lipid based nanoparticles, the lipid moieties are there which are effectively used for biomedical applications. And what happens? This is synthesized like this. If you see this diagram, you can understand that they are normally in the size of 50 to 1000 nanometers. The outer layer is made up of surfactant layer, as I told you. The inner layer is going to carry the drug, and we have the lipids. That means the lipids inside that. Okay, lipids are the necessary things which we have to put into the body. Okay, so like polymeric nanomaterials, lipid possess solid. This is going to have this is solid in nature. This is solid in nature, and this has a outer filmy layer made up of surfactant. So which can be dissolved. Like when this get dissolved, what happens? When this outer layer get dissolved, whatever the drug or whatever the nutrient what you have to carry, it will be placed in the lipid core layer or the solid layer, and this will enter our body. This surfactants and or the emulsifiers, what you call the emulsifiers. Okay, this will be holding this this liquid to a certain extent. During this. In few years back, I saw a video in social media where the athletes were given water pots, especially in that cycle race, Tour de France. What happened is that athletes who are riding the cyclists, they were given water bottles, and they throw the water bottles, And what happened over a period of time, they could find lot of water bottles as environmental impact to the circuit area. I mean the bad race happens. Okay, so what they did, they came out with an alternate idea where they started using water ports. Water ports are just like some air balloons or air bags. Water bags. So which you can just swallow. If you could swallow that, what happens? I mean, after entering your mouth, the bag breaks down and the water enters you just like a jelly. It was like looking like a jelly, like just like a jelly. They take it in mouth, but it's inside. What happens? It's full of water. So these were made up of some biological compounds derived from the sea. I mean the sea microbes and other things are there inside the sea. The planktons. From the planktons, they extracted this and they made this outer layer. Inside layer they filled with the water. But same way, this lipid-based nanoparticles are going to be drug. Inside that, we are going to have drug means here I mean the medicine, the medicines or the protein nutrients, whatever necessary, or any particular thing you have to carry that can be added to this lipid layer, and they can be used for as carriers. Okay, hope you are understanding this lipid-based nanoparticles. Okay, so next we'll look into the next step. We are moving one step ahead now. So we are going to the next step. In this step, we are going to speak about synthesis of nanoparticles. When I say synthesis of nanoparticles are basically classified into two types. One is called as bottom-up approach. The other one is called as top-down approach. Okay, when I say bottom-up approach, it is going to be building step by step. When I say top-down approach, it is going to be breaking down one by one. So bottom-up is building one by one, just like constructing your house. Top-down is like a sculptor making a statue. What he will do, he will break the stones to get a statue, beautiful statue. But in our case, we build one brick by brick to construct a house or any building. So that's what we call it as top-up approach. And the next one we call it as top-down approach. Okay, based upon these approaches, again we have some subclasses. They are based upon their operation, reaction condition, and adopted protocols. But in today's lecture, I'm going to focus on bottom-up approach and top-down approach as the second step. As I told you, in bottom-up approach, it is going to be a destructive approach. Okay, so starting from larger molecules, which is decomposed into smaller molecules. So this is like building up approach. Okay, as we discuss this, I'm moving this. So now you see we have nanoparticle preparation methods. Again, here we have bottom-up synthesis and top-down synthesis. As I told, it's going to be building up something and breaking down something. Okay, in bottom-up approach, we have spinning. Yeah, we as electrospinning, right? Something similar to that. Spinning, template support synthesis, plasma or flame spray synthesis, laser pyrolysis, CVD, that is called, chemical vapor deposition method, atomic or molecular condensation. In biological testing, we have bacteria, fungi, yeast, algae, plants, etc. In top-down synthesis, we are going to look into mechanical milling, chemical etching, sputtering, laser ablation, and electro explosion. Okay, so we will be discussing one by one. But today my focus will be more towards this, towards the light applications, light sensitive light using laser. How this manufacturing can happen. How we can manufacture the nanoparticles or nanotech. How this can be used in nanotechnology. Okay, so in a top-down synthesis technique, we are going to discuss about optical lithography, electron beam lithography, soft and nanoprint lithography, and block copolymer lithography, and we are also looking into something called a scanning probe lithography. Optical, electron beam, soft and nano imprint, block copolymer, and scanning probe lithography. So let's look at this example of optical lithography. So how it is going to work? In this, what we are going to do is we are going to use optical. Optical means photo. Photo means light. Okay, so we are going to use light as the primary source to manufacture this kind of in this nanotechnology type of nanotechnology process. We are going to use light. Light plays a very, very important role. Okay, so what we are doing is, as you can look into the slide, you can understand that we are going to use light as a major thing. So for that, what we are going to do is we will be placing a silicon wafer. Silicon wafer is manufactured separately, and this silicon wafer will be placed first. Then we will be cleaning that silicon wafer by using hydrogen peroxide. We are using this is common hydrogen peroxide. You know that, right? Even in all our homes after this corona, we were using hydrogen peroxide. Hydrogen peroxide is normally used for clinical applications to clean the wound. They'll be giving you something, a black blue liquid, correct? You remember that? A black blue liquid. Even in pharmaceutical stores, it's available. 12 rupees, 20 rupees will be there. Hydrogen peroxide bottles. It is just simple as that. So the silicon wafer will be cleaned by using this hydrogen peroxide to remove the contamination. So because when the silicon wafer are transported or due to some reasons mishandling, sometimes the silicon wafer may have some contaminant agents. Contamination is very, very bad for nanotechnology applications, because even a very minute micron level of presence of this contamination can change the property of the entire application, right? Change the entire property. So it should be free from contamination. That's why you see all these nanotechnology labs will be maintained in a very, very clean environment. Okay, so that's the reason. So in the first type, we are going to see about photolithography, and we have been discussing about placing a silicon wafer, and the silicon wafer will be cleaned by hydrogen peroxide to remove the contamination. Then after this, above this layer, we will be placing a silicon. We will be placing silicon. The basic silicon will be placed as a masking film. Yeah, masking film means it will cover that. The silicon wafer will be covered by the silicon. Then after that, what we are going to do is we are going to use HMDS, that is hexamethyl dislice. So this will be placed, and what happens? This will be subjected to after placing this HMDS, it will be spin coated. Spin coated means it will be rotated at 1200 to 1400 RPM for a few minutes. A few seconds. It will be rotated for uniform spread of this HMDS. That means we are going to frame a layer above this this silicon. Okay, first silicon wafer. Above that, we are cleaning it, and after that cleaning it, we are placing a silicon layer. On that silicon layer, we are giving a coating of HMDS, and this HMDS will be rotated, will be coated uniformly by using by spin coat technology. That is just the wafer and the HMDS will be made to rotate. When they rotate, it takes a uniformly, it gets distributed across the layer of the silicon. So what happens is, after that, it will be preheated. Then you are going to place it in a photo mask. So imagine, to understand the simple technology, you should understand one thing. So as a child, we would have played with the torchlights more. Okay, you remember we have played with the torchlight. So what happens? Imagine you are standing, the lights are off, and you are standing in front of your wall, and you are showing your hand, your palm before the torchlight. So what will happen? When you show the torchlight behind in front of your palm in a dark room, the shadow of your palm will be black in color. The rest of the areas will be appearing bright. Correct? So what that means? What your palm is stopping the light which is falling on it, and only the outer layer of the palm or whatever the light which passes across away from the palm will be falling on the wall. That's why we shadow play, right? Normally we do the shape of a dog or a bird or something like that. When we are using a torchlight in the wall, when the power goes off, we normally play like this as a child. So that is the technology behind this optical lithography. So here also what happens, now you could see in the slide what happens. There is an illuminator. This illuminator is nothing but your torchlight, and that is a mask. This mask is going to be your hand or the palm. Okay, your hand or the palm. Okay, so now what happens when the light is projected? This in this case, what happens? There is some circuit kind of some transistor or some circuit kind of design is made. So wherever you find this thing, the light is not allowed. So only in the remaining area the light will pass. Only in the remaining area the light will pass, and this is focused on the this will be focused on the silicon layer which is placed above the silicon wafer, and this is focused by a lens, condensing lens. A condensing lens will be used, and this light rays, when they cross this, they will cross. These things will be in this area. The block, it will not allow the light. It will be not transparent, so it will not allow the light to pass through. So it will be falling on the photo on the pattern. So this pattern will be coming here. So if you zoom and look like this, it will be like this. So here, if the blue color area, what happens is that the light is not allowed, whereas in the pink color area the light was allowed. That means here it was transparent, so that's why it is pink in color. That means it is photo cured, because of the light, the silica or silicon, whatever is present here, it was cured, whereas this layer, it was not cured. Okay, so what will happen in this area? So now what we'll do? So whatever is in pink color has to be removed now. So what we are going to do? We are going to use some etching agents. Sometimes these etching agents are gas type etching agents, or we may also use some solutions to as etching agents. Okay, so what will happen? There's normally silicon dioxide is formed above this. So the silicon dioxide will be removed by using this etching agents. So once they are moved, they will be looking like this. This will be like a circuit board or circuit of some transistor or something like that, transistors. So if you want to make this more, you can add some impurities. When we add impurities, we call them as the process doping. So you can add some impurities to improve the characteristics or for the desired characteristics, you can add the desired impurities to give it more properties. So like that, you can make this as a semiconductive devices. So this is one example of photolithography. I hope you understand this photolithography principle. So this is normally used for producing chips. Okay, for your mobile phones or other advanced electro gadgets. Okay, so if you want to build layer, you can build layer by layer. Above this completed one time, you can build another layer. So because of this technology only, all our mobile phones are becoming smaller and smaller day by day. Okay, so it's what are the advantages? It's very easy. It's a very easy process, but it's costly process. We know that. But the problem is with playing with the sensitivity of the light source and the curing time, what it takes for the other areas. And we would maintain a clean room environment because no contamination is allowed in this process. So you should be very, very careful about this type of lithography process. Okay, so this is about optical lithography. Next, we have the next technology called as electron beam lithography. Okay, here in electron beam lithography, it is hereafter all the technologies are going to be similar. Only thing is that the source of light here it is going to be different. In the last case, we are using just a plain light. Okay, of course, I forgot to tell you about this. This optical lithography technique is nothing new. It was also earlierly used. Earlierly, it was used to print our T-shirts. Screen, we call that as screen printing. So here, in case of screen printing, what will happen? In this area, if imagine this is the design you want to make on your T-shirt. What will happen is the ink will pass only through the white, like this. Okay, take this example. The light will, the ink or the dye will pass only through this. This area will be white in color. Imagine you're printing on a white T-shirt. This will not be printed. This will not be printed. If you move the paint, a layer of paint above this, the paint will pass only through this, and it will be printed on your T-shirt. Okay, so that is called screen printing. In case of printing in your clothes, we call screen printing. Okay, or just like taking stencils. Taking stencils while taking a stencil. What you do? This is just a stencil. This mask is nothing but a stencil. This mask is going to be a stencil. Imagine like that. Okay, so now let's go about the electron beam lithography. As I was discussing, only the source of light is going to be vary. Otherwise, the technology is going to be the same. Okay, but this is more extremely accurate method compared to the optical lithography. Okay, so what happens is here is same. We are placing a silicon layer. Above that, we are placing a resistant layer. And what happens? Above this, we are going to pass the electron beam. Electron beam we are passing, and what happens is that, say for example, if the electron beam is passed here, this layer will be removed. Okay, this layer will be removed, and this layer will be left out. This layer will be left out. Okay, this layer will be left out. This resistant layer will be left out. So what happens is now, and above this we are going to deposit the metal. This is another layer, the metal layer. So what will happen now? So in the post-processing stage, what happens when you deposit the metal, and when you remove this, when you remove this resistance, resistance by etching, by doing some etching, or by etching or by dissolving the unwanted. Etching means what? Removing the unwanted thing. So here this resistance is not required. We require only the metal to be deposited here. So this process is called as electron beam lithography. Okay, this in the post-processing stage we can remove this. We can remove this. Similarly, we can build upon, depending upon our requirement, we can build upon one by one layer by another layer. Okay, so this is electron beam lithography. So the next we have something called as soft and nano imprint lithography. Okay, in soft nano imprint lithography, there are three types primarily. One is the plain nano imprint lithography. We have ultraviolet nano imprint lithography. We have thermal nano imprint lithography. There are three types, I repeat. Regular nano imprint lithography. Other one is going to be ultraviolet based. The third one is going to be thermal nano imprint lithography. Again, we have several types of with this. There can be plate to plate, roll to plate, roll to roll, plate to plate, roll to plate, roll to roll. This is very simple. I'll give you very simple. I'll explain you in a simple way. Okay, so here you take this example. This photograph what I showed here in the slide. It's going to be based upon two things. One is the substrate. This is the substrate. Above this we have a photosensitive. In this case, I'm using a titanium oxide film. It's the titanium oxide film is that. So this is the fundamental. This is basic for all the things. This is the fundamental, or this is the base for everything. Everywhere, all these three types, you will have the substrate. You will also have the titanium oxide precursor layer above this. Okay. So now what happens? We are using a polymer mold. In this case, I used PDMS. Okay, then we have polyurethane. So we have two types of mold. So what will happen is that this is just like making an impression on removing the unwanted things, making an impression and removing unwanted areas. So what happens is that when I put a mold like this, so imagine you take this example in the PDMS. So here I am putting a PDMS mold like this. So what happens is that, and this is a substrate. This is the photosynthesized titanium oxide above this. So this layer, this blue color layer is what? Titanium oxide layer. So I'm putting this PDMS mold there. So now what will happen is that when I pass the ultraviolet rays above on this substrate, what happens is that this area, so you could see some pillars here. These pillars are not cured by the UV rays. The rest of the areas will be cured by the UV rays. So now what will happen after etching or after removal of this? You can find that find the titanium oxide here deposited here. Same way here it will be, since the mold shape is different, it is going to be like lines. lines. So this is one kind of fabrication, same titanium oxide only, but depending upon the mold and depending upon my etching activity, I'm going to, here I removed this particle, this lines. Here I removed all this, all this. So that's why this is called as soft imprint nanoparticles. To make this imprint, depending upon the mold shape, we call it as plate to plate or roll to plate. Roll to plate is just like to massage your body, there will be a roller, what you use, roller type of massage to your back. If your back, you have a back pain, sometimes this, if you go to some tourist places, they'll be selling this massage, right, made up of wood. This is something similar to that only. There's no new technology or something like that. It is very simple like that, just to speed up the process. Plate to plate, this example what I showed is plate to plate, one plate next to plate, like that. So in a roll plate means one plate will be the above the another roll. I mean, just like we're rolling, it will be making the imprints and it will be curing, and it will be going in a conveyor. The next is fully rolled. It's just like rolling a sugar cane. The substrate passes to the middle. The rolling, as the rolling happens, the imprints are going to be made. Okay, it is cheap and cost effective compared to the other methods. Okay, so the next type we have is called as block copolymer lithography. What is this block copolymer lithography? Okay, this is again, this is very interesting one. So here, imagine this is like mixing two things. Okay, so to understand this, to the bottom of the slide, you could find a diagram, a small diagram. This diagram will explain you what is this block copolymer. This block copolymer, as the name indicates, copolymer, there are going to be two polymers. Here there are, imagine there's yellow is one polymer and the B is, or the blue color is another polymer. Yellow color is one polymer and blue color is another polymer. So what I'm doing is I'm going to do a spin coat. Again, I have a substrate, I have a resist. Above that, I am putting this. Again, above this, I'm putting this spin coat. I'm going to spin this and I'm going to coat this. So you could find this blue and yellow block copolymer deposited on this. So next, what we are doing, they are subjecting into a annealing process. Annealing. The annealing means we are doing this annealing process. We are going to cure the process. When you're curing, and when you're washing it by some etchant, what happens? Only the necessary things are left out. The remaining, after removing this unnecessary parts, it will be removed. So again, we can do this. If you want, you can do this stripping process to retain only what is required. So this is how we do the copolymer block copolymer. Here also it's like this. We have a silicon nitride. That's a base. Everywhere the silicon is preferred as the base, and here I use a ozonated sample in this case. Then it's after doing some etching activities, I'm going to get some holes. If I want some holes, I'm using this kind of technology, holes and dots. So this is the difference. So you just remember that in block polymer, there are two types of polymers can be deposited. So the two types of different nanoparticles can be deposited by using this technology. Okay, this is low cost, of course, but this is very easy to make for copolymers. Next, we have scanning probe lithography. In scanning probe lithography, this is something similar to our 3D printing only, where we have a current control system and the force control system. But here, the sensitivity of the tip is going to be very precise. Even it can be 1 micron or less than 1 micron. This 1 micron tip, what is going to do? It's going to be actuated by the cantilever. It's like a cantilever system. There are some actuators and controllers with the PLC to actuate this. So wherever it's necessary, it's going to make. So the previous technologies, what happens? Some deposition is going to happen, and you're going to remove the unwanted area. But in this type, it is going to print, or it's going to remove only where it is necessary. It is going to print only where it is necessary. So mostly this technology is costly because the control of this cantilever type of scanning probe is very difficult, and you need and this is also a piezoelectric. Piezoelectric means, you know, this is going to resonate depending upon the frequency what you're going to supply. Is going to resonate, and its axis can be controlled just like a CNC machine or just like a 3D printer. The scanners direction can be controlled along X, Y, Z. So when this piezoelectric is activated, this cantilever beam is going to get actuated, and this is going to print on on the semiconductor substrate what is present here. So this is about the molecular resistance. This is going to print, and only these layers are going to be used. The remaining layer can be washed again by etching technology. So this is one kind of technology. But here we call this the stand-up distance. The distance between the substrate and the tip plays a very important role. Similarly, the field emission scanning. Okay, so the emission or the light control, what is going to be made here? The what do you call the frequency or the resolution of the field emission is going to be very critical parameters which you have to control in manufacturing this kind of lithography method. So next we are going to see about the other 5 types of process, that is for bottom-up approach or bottom-up synthesis techniques. The first one what we are going to look into called as atomic layer deposition. Atomic layer deposition. So here what is going to happen is we are going to deposit some kind of deposit atoms on a layer for obtaining different properties. So I have a short video for explaining this atomic layer deposition. Let's see if we can play this because it will be monotonous if I'm talking only. So let's play a small video. Okay, so so I think you understood like what is atomic layer deposition. So we are going to deposit the layer by layer of oxidized layer of metal particles or the necessary nanoparticles above the substrate or the metal on which you have to do this. So normally atomic layer deposition will happen is cost effective, and we are going to use a vacuum chamber in this process. Normally silica or titanium dioxide, they're all deposited by using this process of atomic layer deposition. So in the next process is going to be sol gel nanofabrication. So in this sol gel nanofabrication, this is another area where you can focus for your PhD in a detailed manner. So this is again what you use for mostly for ceramic composites. Here this kind of sol gel fabrication is very famous. So what is this? In this process we are going to have two phases. Okay, sol gel. Okay, sol means solution and gel means is going to be a gel like diphasic system. Okay, diphase means two phases. It's going to exist in two phases. Okay, that's why we call diphasic. Gel like diphasic system is going to be that. Sol gel. Sol means solution and something like jelly like kind of things in two phases we are going to absorb. Okay, so what is this? So as I told you, the sol gel process is for ceramic composites. Again, you should understand that this sol gel nanofabrication has three primary steps. One is hydrolysis. The next one we call it as condensation. The third one is drying. I repeat, we have three steps of process in any sol gel nanofabrication. One is hydrolysis. Next we have condensation. The next one will be drying. Okay, so how this happens? This is normally for inorganic metal salt or organic alkoxide here. So as I told you, there are two phases. One phase will be the reinforcement. One phase will be the reinforcement, and the next phase is going to be the matrix or the liquid. Okay, this reinforcement and matrix layer will be subjected to polymerization process, and by that polymerization process we will be producing a gel-like structure. Again, when this gel-like structure is subjected to heating by a furnace or some other process, we will get, or this heating we can call as drying also. Then we get something called as ceramic matrix composites. So this is the sol gel process. So what we are doing is we are subjecting this alkoxide to hydrolysis. Then we are doing condensation by polymerization process. Then we are producing a gel-like substance. Then this gel-like substance is allowed to dry. So I told you hydrolysis, condensation, and drying. So these are the three steps. So by hydrolysis, here I mean we are mixing with some water or other solution. Then we are making it to condense. Then we are making into drying, and we are making by heating. Then we are making the composite. Okay. So to understand this, I will normally give this example of making dosas. You know how to make a dosa, right? So the same process is going to be applied for sol gel. So imagine this metal alkoxide solution as your batter. Okay, how you produce this batter? You mix dal, rice, and other items. You make it to you put that in water for a long time. Okay, immerse it for a long time, and you grind it, and you produce that, and you keep it in a vessel. You mix salt, and you will wait till the morning for it to ferment, and it will precipitate some white things. Okay, so you will remove the excess water from the batter. Okay, you will remove the excess water from the batter. Then you take the batter, you put it in the fridge. Then after for evening, you will take that from the fridge, and you will put a tawa on your stove, and you will heat the tawa. You will put the batter on the tawa, and you will heat it, and you will take the dosa out of the pan. Simple. It is also a sol gel process. How? I'll tell you. So here what happens, the metal oxide solution is the batter. It is allowed to undergo the process called as polymerization. In case batter, we call it fermentation. In case of metal alkoxide, we call it as polymerization. So now the solution is developed. So what you are doing, you are going to make it precipitate. That means you are allowing it to ferment for a night, and in the morning you will remove the water, excess water, whatever is there in the solution. So that is called as, so that you will have a uniform particle. That means it will settle down. Just like the curd. If you're making the curd, the unfermented curd, the excess water will be removed from the curd, and you get the thick curd, right? So that is the uniform particles. Then you can keep in the fridge for gelling. Like it will be staying like a gel, like it will be in a semi-solid state. Then what happens? You'll get aerogel. Okay, this aerogel is now put on the this aerogel is now put on the heating pan, the dosa pan. What happens after heating? It get condensed, or it's like we call as polymerization, right? Condensation. This condensation process is happening, and because of the condensation process, what happens after drying, that is by heating, you will get the dense film on the metal to be deposited, or generally for heating, you'll get the dense ceramic out of this. And if you are just like that, after this process, you are using some extraction solvent, you'll get the aerogel. So now I compared the process of making dosa to a sol gel process. Both are similar, except that that's just an example of how you do the sol gel process. Don't take it that example seriously. Just for easy understanding, I gave you that example of making dosa for the sol gel process. What you are doing, you are taking the metal nano oxide and you are dissolving it with water or salt, making it a solution. After the solution, you are removing the water, so that it becomes the precipitates are only available. Then after that, you are allowing it to make it as a gel. Out of this gel, what happens during this gelling process? Also, it will leave out some precipitates. That's why it looks like a gel. After this gel, you are going to condensation. You're going to do condensation. So by doing condensation, only the aerosol is available. By heating it, you are making a dense ceramic. So I told you hydrolysis, condensation, and drying. Same way. Otherwise, you can straight away coat this aerogel here, the solution here. So after heating it, only the extrogel film will be there. This extrogel film will be deposited on the heated substrate. So this is how. And if you are using it directly, we get the plain aerogel. Okay, so this is how we do the sol gel process. This is a this is used mostly for ceramic thing. As I told you, it's going to be used mostly for ceramic thing. But we can't measure the quality. Zinc chloride can be produced by using the sol gel process. So you can read further to understand the sol gel process. And then next we have something called as molecular self-assembly things. Here, depending upon the pattern, right? So it allows for the nanoparticles of less than 10 nanometers. Okay, they can be stretchable and they can automatically assemble. It's like it's a self-assembling, right? So the molecular particles, when they're introduced into this nanoparticles are introduced, their molecules are sometimes able to arrange themselves to get the desired mechanical properties. So that's why we use this process called as molecular self-assembly. Okay, the next step we'll be discussing about the physical vapor deposition and chemical vapor deposition. So as I told you in the first few slides, I told you about this process of manufacturing nanocomposites using CVD and PVD. So what is that? So normally this chemical vapor deposition is used for coating the tools. Coating the tools, I mean single point cutting tool or multiple point cutting tool, that can be there. The process is very, very simple. You have a reactor chamber. Okay, in chemical vapor deposition, you have a chamber. Chamber means a condensed shell kind of thing. Condensed shell. or a vacuum chamber, right? Normally it's going to be vacuum chamber. So what happens is that there the metal or the on which you want to apply the coating, that will be placed inside the chamber. So here in this chamber, what you're doing, it's a vacuum chamber. You're putting the item or the part which you want to electrocoat on this coat. We have here inside this, what we are doing, we are passing the oxides. Normally we will be passing the oxides which has to be coated on the on this, right? So otherwise, in this case, I told you that we are using metal precursors. Metal precursor means which item if you want to deposit titanium, we are going to pass the titanium gas, like that. Titanium dioxide will be passing. So here we are doing this. So this electron, this happens by electron source. In this crucible, the metal is placed. The metal, for example, titanium oxide, that is placed, and through electron beam, this is allowed to evaporate. Once you make this to evaporate, this comes as a gas and it gets deposited on this item, and the remaining things will be captured by this vacuum chamber. So this is one small example of physical vapor deposition. I was speaking about chemical vapor. Sorry, I just changed it to physical vapor. Physical vapor means physically you're passing this vapor and getting deposited on this. Just imagine, this is very simple. You are boiling some water and you are putting a plate on top of the boiling water. What happens? The vapor is absorbed on the plate. Say for example, you're boiling the water and putting a cloth on that. The cloth will be fully be absorbed with water particles, or it will be get wet easily. So that is the process of physical vapor deposition. In case of a chemical vapor deposition, the same setup. You forgot about the crucible. Instead, the gas is passed. Just like how you saw the atomic vapor deposition model. In chemical vapor deposition model, the gas will be passed. It will be deposited on the item which is to be coated, and the excess will be removed by using the vacuum pump. So that is how it will happen inside the flow of the oxides, and the flow of the waste gases outside will be controlled by a PLC unit or programmable logical control unit. So it will be controlled process. It's not just like that we send some gas inside. When we take out the part, it will be coated on. Here the process is totally under a controlled environment. But here we should be very careful about depositing the impurities. Okay, we can coat metals, ceramics, semiconductors, insulators of polymers, and you can use for nanofilm coating. Anything can be coated. Most of the items can be coated using CVD and PVD technique. In PVD, that's going to be a direct deposition of physically you're going to deposit something. That's the direct deposition method. Just like I told you, the heating the water and placing a cloth above it, or a plate above it. Similarly, in case of chemical vapor deposition, it is going to be the gas which is going to enter, and the waste gas which is going to out. The excess gas which is not deposited, on the plate or the item which is being coated will be removed out by using the vacuum pump. Only this is the difference between the PVD and CVD. This is the example of CVD. As I told you, this is the controlled chamber. The argon here, in this case, argon gas is passed, and these are the particles which are deposited on the small samples. What is placed here? Okay, so these are the small samples. So this gas passed through, this gets deposited, and the excess gas is getting removed. Okay, so that's what. And in this process, in both this process, the samples can be rotated. The samples can be completely rotated inside the chamber itself. The particle will be rotated because it has to be deposited around on all sides of the substrate or the sample on which you are doing the coating. So to make it a uniform coating across the body, the samples will be normally rotated at some RPM, controlled RPM, for the oxides to get deposited on the sample. So that when these are done, for if you want to have some coating for improve the hardness or the other properties, normally they are done. So especially you will have this titanium coated single point cutting tool or multiple point cutting tools. So depending upon the requirement, the oxides will be passed and the sample will be rotated around to get the thing. So here that's why we use the spin coating technology will be used here. Okay, so this is one example of CVD. This case is the example of PVD, and this is the example for how CVD is done. Okay. So the last type is called as DNA scaffolding. So this DNA scaffolding is used mostly for biotechnology applications, where these scaffolds, these are scaffolds are nothing but the arrangements, right? The arrangement of nanoparticles, how we are going to arrange here. This is normally this DNA scaffolds are less than 100 nanometers. Okay, so these are used for, as I told you, for mostly for drug delivery systems. They use this DNA scaffoldings. They're allowed to enter your DNA or the blood directly. So these are one type of DNA scaffolding. So again, when you see the applications of nanoparticles, there are very large number. You can't even count where nanoparticle applications are. It is available all. Nanoparticles have already taken deep roots in all items whatever we use. It's there in structurals. It have nano division sensors, coolants, lubricants, fuel cells. Fuel cells is where nanotechnology is highly picking up. Then hydrogen storage medium, biological systems, sustainable energy systems, batteries. Okay, because of batteries, the size of the cell phones are also coming down day by day. So I given the wide examples of applications of nanoparticles here for drug delivery, antibacterial activation. Even this corona time, we are using a lot of face masks, where nanotechnologies again can play a very vital role. Nanotechnology, I told you, by electrospinning, you can manufacture a face mask which can not prevent particle droplets of less than 1 micron or 2 microns, very minute particles also of say for example particle matter of size 10 or 2.5, even they can prevent that. So you can think about some projects where you can use this nanotechnology to manufacture face mask for water capturing from the or pollution control. So all these things are there. Even we are working on in VIT, we are working on my team is working on one project for producing face mask using electrospinning technology by using natural and synthetic polymers. We are using chitosan as one of the reinforcement in that, and we are working in that area of nanotechnology. We are trying to produce face masks which can prevent coronavirus, but I don't think we will be able to reach the level of coronavirus. At least to some extent, we can stop the spread of airborne microorganisms. So this is what we have for today's guest lecture. If you want to continue, I can continue with the tribological applications, but I guess I'll take some questions now.
Sir, thank you, sir. Thank you. Very nice presentation, sir. I request our participants, if you are having any queries, please unmute yourself and you can ask questions to our resource person directly. Or you can type the question in the chat box. We will ask for you.
Hello, sir. Good afternoon.
Good afternoon.
Yes, sir.
I'm Ramesh Kumar from NDK-IST.
Okay.
Sir, my question is how the nanoparticles used in renewable energy sector. You mentioned that there are some application of nanoparticles in renewable energy. How it is used in the wind turbine blade design?
Yes, sir. Yes, sir. Sir, to be frank, I'm more into composites. Okay, so but I will tell you whatever I know from my end on windmill aeroblades or in generally about renewable energy. Okay, in windmill, what happens is the structures of the windmills are very normally huge, and to manufacture this blades, they are using they have changed the materials. Say they are using carbon nanotubes for manufacturing the wind turbine blades. Okay, so you'll find nano carbon tubes. Okay, carbon nanotubes are applied in manufacturing blades. Then again in coating, you could see a layer of coated nanoparticles are coated on the surface of the wind turbines to prevent corrosion. Okay, again to resist the force, to make it light, at the same time to make it strong, they are using this nano coatings on the layers. Sometimes nano coatings are given considering the thermal variations where these windmills are installed. Sometimes these windmills are located mostly in the coastal areas or in above the hill, or sometimes in deserts where depending upon the wind velocity they are being installed. So considering the environmental conditions where they are located, different types of coatings are also given. I believe I have answered your question, sir.
Yes, sir. What kind of the nanoparticle coating to avoid the corrosion kind of things?
So normally some kind of oxide coatings will be given, sir. Oxide oriented coatings will be given.
Okay, sir. Thank you, sir.
Okay.
Thank you, sir.
Thank
Sir,
you.
one more question from chat box, sir. Shall I proceed, sir?
Yeah.
Sir, this question from Professor Prem. Difference between graphene and graphite.
Okay.
I think difference between graphene and graphite.
Okay, sir. Okay, sir. I got it, sir. So
sorry, sir. It is the extension of question is tribology aspects of difference.
Tribological aspects of
difference.
Okay. Graphite. Okay. Graphite and graphene both are made up of carbon. Okay. Only the atomic structure wise they have a difference. But graphene are used for high strong applications compared to graphite. Graphite are normally amorphous and they can break down easily. Graphene are very stronger. I mean, compared to CNT, I was speaking about carbon nanotubes. Compared to carbon nanotubes, graphene is also finding its application in a lot of tribological applications, especially in automobiles or in helicopter rotors. Wherever rotors are there, rotary equipments are there, you can find this graphene is used as a lubricant. Okay, so when you deposit this thing on this nanoparticles inside or giving a coating of this graphene coating is you are applying or reinforcing the metals with this, it becomes a self-lubricant, self-lubricating things is possible. So this can be used as a self-lubricant, graphene. Okay. Not graphene alone. There are different types of self-lubricating composites are now available.
Thank you, sir. I request once again participants. Sir, one more question, sir, plus from chat box. Sir, graphene, any manufacturing and testing available in India?
Yeah, it's available. You can check the Sigma Aldrich. There's one website called Sigma Aldrich where they give quality products of graphene. I think that will be easy source for you to purchase. Regarding testing, there is no specific testing for graphene, but you can go with based upon your application. You can do it. You can do the testing. Okay, depending upon application. For vibration application, you have different set of experiments you should do. And for morphological studies, you have, if you're just doing morphological studies, SEM, TEM, and all these things are there, right? Thermal applications, you do TGA and all these things.
Okay, sir. Thank you, sir. Sir, another question, sir. Sir, will any kind of nano coating paint in radiators increase their efficiency? And if yes, which kind?
Okay.
Shall I repeat, sir?
Yeah, I got it. It is from the Deeptam Roy Chowdhury.
Yes, sir. Yes, sir.
I could see the chat box. Sir asks, will any kind of nano coating paint in radiators increase their efficiency? And if yes, which kind? Okay, sir, I'm not very good at this. My research. I told you I'm just using nanoparticles for reinforcements in my composite applications, and I'm just dealing with a few cases of tribology. I'm not very good at that, but I can't tell that nano coating will improve the performance of radiator. It will, of course, it will safeguard the radiators. Okay, in heat conductivity or heat transfer applications. This in radiators, of course, nano coating is available. People are doing nano coating, but personally, I'm not good at it. So you can ask a better expert for that.
Thank you, sir. Sir, another question from Shankar, research.
Shankar, yeah, photonic crystals on mechanical applications.
Yes, sir. Yes.
Okay, yeah, photonic crystals. I think I take it for as I don't know in which specification Sarah has asked this question, but photonic here I take is just mostly like solar panels applications. Someone was asking about what is the application of nano in renewable energy. So all your solar panels are made up of this thing. Even when you say renewable energy nowadays, we are focusing on batteries and other things, lithium-ion batteries, or we are making to make even the fuel cell batteries, and we have another advanced versions coming up. So all the places now nanotechnology is slowly taking its place.
Sir, another question, sir.
Is nanotechnology useful for quantum hardware?
Yes.
Sorry, again, I am not very good at that. I know only about quantum dots. As I explained you in LCD TVs, we are using quantum dots, and almost all your mobile phones have quantum dots for wherever more clarity in picture is required. I'm not sure about quantum hardware, what you're specifically asking. Even if you want, I will check the answers and I can get back to you.
Thank you, sir. I request once again participants, please unmute yourself. You can ask any queries directly to our resource person. Sir, it seems no questions. Shall we close, sir?
Yeah.
Yes. Thank you very much, sir. Your presentation added more value for this STTP program. Really, your presentation got overwhelming responses, sir, through YouTube link also. Really, it is excellent presentation, sir. The takeaway from your presentations are high. You have started with the nanoparticle, nanocapsules in that hydrophobic, hydrophilic, and fullerenes, carbon-based nanoparticles, metal nanoparticles, polymeric, ceramic, liquid-based, synthesis of nanoparticles, that too in the two types, a top-down and bottom-up synthesis approach, various techniques. Really, it is a very, very nice presentation, sir. Thank you very much, sir. Thank you, sir.
Thank you for the opportunity provided. Thank you, Madhi sir, and thank you, Guru Magesh and Hemant sir. Thank you very much. I'm thankful for this, your management also, for giving me this opportunity to present this on topic on nanotechnology. Thank you so much.
Thank you, sir. Thank you very much.
Thank you. I thank the participants also for patiently listening to me for more than 1.5 hours.
Yes, sir. Yes, sir. Participants are the very important person. I request the participants tomorrow our session will start at as usual 9:45. Today's session is over. I request our participants tomorrow we will rejoin again at time 9:45 a.m. morning session. Sir, Rajesh sir, can you display schedule, sir? So that the participants will know the details of tomorrow's program. Tomorrow we are having a doctor. So I need some more zoom outs. It is small, it seems. Thank you, sir. The topic is application of nanomaterials and heat exchanger. Our resource persons are Dr. G. Kumaresan from Vannariamman Institute of Technology, and afternoon session it is from Harish Barshila from National Aerospace Laboratories, Bangalore. I request all the participants please rejoin time at 9:45 a.m. Here we will continue for tomorrow's session. Thank you, sir. Today's session is over. Thank you very much. Thank you for all the participants who have till the end. Thank you, sir. Thank you.